Okay, we will now take up the remaining features of stepper motors. To recall what we have done in the last lecture was that stepper motors are not a continuous rotating machines. Stepper motors have a long history, although they have become very important and popular in the last few decades. Okay. They are produced in millions. They are mostly small rating, there are not many stepper motor which you can't hold it in your hand. I mean they are of small size, right, and they are used for lot of control purposes to produce mechanical movements, mechanical steps, right, and they are used in process control, they are used in aeronautics, they are used in automobiles, they are used in ships, they are used in aircrafts, they are used in machine tools, they are used in robotics, they are used in mechatronics. Okay. So, wherever you require a small moment they are used, and it works in the principle of alignment of the rotor with reference to stator magnetic field. Okay. And the types which we have understood are the permanent magnet and variable reluctance. Okay. The two types of stepper motors which we discussed, okay, and there were comparisons. The permanent magnet will give you more torque, whereas variable reluctance will give less torque, but it is simple. Okay. And there are different variants of this we have seen, and now we will look at a little more analytical theoretical background to these machines, of course within a limited issues. Okay. So, we have seen that the basic configurations of this will be this is a hybrid stepping motor where it has a combination of variable reluctance and permanent magnet. Okay. And this is also a hybrid stepping motor for those who require some recall. Okay. Right. And this has stator and rotor windings with the magnets on the rotor side and a variable reluctance, and this is a combination where you can have PM here and VR here, right. So, this is what we have tried to understand. Okay. Now, in those variable reluctance ones, stator stacks are aligned, rotor stacks are displaced by half tooth pitch, and stator and rotor tooth pitch is same. Okay. And the stator tooth pitch can be made larger to reduce return torque and increase the positioning accuracy. Return torque is the torque which it will be it can experience at rest unexcited in PM machines, and the maximum holding torque is when you excite a machine, when you excite a coil, how much maximum torque you can apply on the shaft before it slips out of step. Okay. So, these are some definitions. So, we have defined what is the step angle, what is the pulses per second, okay, which will have a number of pulses per second will definitely decide the rotation RPM, isn't it? Just take the frequency in the stator of a synchronous machine decide the RPM. Okay. So, we have these features. Now, there are the type of windings, there is monofilar and bifilar windings. Okay. Monofilar is a single winding wound on the coil, a single winding which will produce a single pole, okay, that is a monofilar windings. Okay. Bifilar is there are two identical overlap windings wound on the same pole, but one in forward direction, other is in backward direction. So, in bifilar you have two windings on the same poles, okay, but one may be having a dot position which is opposite to the other. So, if you pass a current through one, it will produce a north pole south pole. If you pass a current through other, it will create a south pole north pole. Okay. So, two overlapping wires are wound as one wire effectively giving two windings. One coil say belong to phase 1, other to phase 3 in typical 4 phase system. So, bifilar winding is to excite poles by alternating polarity. Okay. So, the same poles, if you have this, sometimes it may become north pole, another time it may become south pole, depending upon, because you have two windings, okay, which is excited on this. Is it clear? Okay. And there are solenoid coils used in multi-stack VR stepper motors. I think you have seen, I think let us see whether we have this solenoid coil. This, yeah, this is a solenoid coil. So, it just goes round like this, okay, in one stack. So, one coil just wound one or the other, okay, right, one phase, right. So, there is no multiple coils here, only one coil in this, and as soon as this is excited, rotor aligns with reference to the stator. Then it is a multi-stack, other stack will be excited, this gets shifted with the axis, okay. Right, okay, let us see. Now, there are also hybrid and single stack VR motors which has monofilar or bifilar windings. Okay. So, for hybrid and single stack motors, either you can use a monofilar or a bifilar windings. Okay. Now, what are these monofilar? We have been talking about it. This is a monofilar winding A. So, there is one coil here. If you pass a current through this, okay, then it will produce unipolar excitation, is not it? It cannot change the poles when once you this is one coil per pole, okay, and which is switched by a transistor like this. Okay. Then this is also monofilar. That means monofilar is you just put on you just one coil like this, right. So, and it can, in this case it can only pass a current in one direction, there is no way you can pass a current in the other direction. Now, this is the same coil, but you have a bipolar excitation using H bridge, this is an H bridge, looks like H. So, you can pass a current in what way? In both direction, I hope. You can pass a current like this or you can pass a current like this, yes, right. How do you pass a current like this? Which are the switches to be operated? Supposing you have 1, 2, 3, 4. So, if you have 1, 4, so will be I1, is not it? Is it okay? And if you have 2, 3, so that will be other direction I2. So, if you this and this are excited, the current will flow like this, simple. Okay. Then third one is bifilar and bipolar. This is also bipolar. So, here this is on the same pole, but the switches are less. Okay, same 1 or 2 switches are there. So, if one is there, this will be the current I1, and the 2 is there, then this will be the current I2. Now, you will see, since they are wound in opposite direction, with I1 gives you here north pole south pole and I2 gives south pole north pole, is not it? because you have, it is wound in a different way. You see, the polarities are like this, opposite. So, two parts, okay, are made, one in maybe clockwise, other would be anti-clockwise on the poles, right. I hope there is no problem on this understanding. So, we have these are the different types of windings in stepper motor. Okay. There could be, now you can have a single phase excitation or a wave drive, you can say. So, one at a time, like a wave, it is called a wave drive. If you have multi phases in the stator, you go on going in sequence 1 2 3 4 1 2 3 4 1 2 3 4 like this, right. So, one at a time you excite, or you can have a full step drive or two phase excitation, you can have 1 2 2 3 3 4 like this, see, is not it. So, here it would be like 1 2 3 4, here it will be 1 2 2 3 3 4 4 1 etc. Or it could even be a combination, okay. And half step drive, 1 and 2 phase excitation both can be there, you can have 1 1 2 2 2 3 like that is also possible, okay. Then micro stepping means small steps with continuously varying motor currents. Okay. These are different ways of switching that you can effect in a stepping motor. Okay. Okay. Now, there is a full step drive. That is two phase excitation. Now, for example, at this position A, so you have 1 2 excited, say. Now, it will align with the center of these two, okay. This is what you have the alignment, say. Let us say if in this case, I think we will have to, let us say if this is I think north south or something like that, I think if this is 1 2, what will be this, because it is 2 3, because it has come here, the south has come here, right, and here it is where it is, I think it seems to be identical, is it? No, this is other way around. Yeah, it should be, this is basically 3 4, okay, 1 2 2 3 3 4, this should be 4 1. Huh? Yeah, I think there is a mistake here. So, this should be, I think it should be, this should be the south, this should be north, let us say, okay. This is south and north, okay, right. So, you change this. Now, I think it is obvious that you can have a two phase excitation and the rotor, even it is a permanent magnet, will have a 45 degrees shift. How much each step will be 45 degrees, is not it? Is it clear? This is one way of excitation. So, you can see for different positions, and another thing is you can even try to have change the directions of any one also. Okay. If you say S1 positive, it will have another angle, S1 negative also it can have depending upon the bifilar arrangement. Okay. Let us see. So, switching mode by two phase excitation, full switching mode will be, so for one position you can have 2 can be plus and 2 can be minus. So, you have S1, S2, S3, S4, you can excite in a suitable way. I think there could be even it is not necessary only 1 2 should be excited, even 3 4 can be excited also, but it depends upon which direction. Okay. So, I think we will not freeze it, I will put it as a question mark here. So, all can be excited also, 2 can be excited also. Okay. So, for example, here is okay 90 degree excitation, that means you can excite both 2 at a time. So, here in position 2 you have this is minus, this is plus, 2 plus and 2 minus, 3 2 minus and 2 plus, and 4 you have 1 2 minus and 2 plus. Okay. So, you I think it is simple logic, you can work it out without a big deal. Okay. If you have 4 poles in the stator and 2 poles in the rotor, or 4 coils in the stator and 2 poles in the rotor, you can have combination of switching that you can effect to see that the rotor positions can change, and obviously each one will give different performance in terms of the holding torque and return torque, etc., because that is what will be how much it can hold depending upon how much MMF you are able to produce to the stator windings. Okay. Now, this is another combinations, you have 0 degrees, and you have 45 degrees, you have 90 degrees, and again you have shifted 135. I think let us say 0, 45, 90 and 135, okay, like this. So, you can just okay, by different excitation you can get to different steps. Is it clear? Okay. You can create 45 degree step or 90 degree step or whatever, okay, like this, right. So, it has all gone into different angular positions. Okay. I hope it is not a big deal how it aligns. So, the step angle in half stepping mode will be, we have already seen, it will be 360 by 2 MNR, where M is the number of steps, poles, and this is the number of steps, etc. And then micro stepping drive, currents in the windings are varied to be able to break up one full step into smaller discrete steps. Many times micro stepping means you can have smaller steps are possible. Okay. Now, we will go a little detail, not too much. I have taken a, is it a stepper motor or PM or variable? Can it be PM or can it be variable or both? It can be. Now, you have a rotor, I have not put the slots. Okay. Rotor I have not put the slots. Let us say this is the rotor position theta m. Okay. And there are coil 1 here and minus 1 here, then 2 here and minus 2 here. So, you can say that it can enter here and come out here, I1, and similarly it can enter here and come out here. Okay. So, you can create the fields. If you excite one, where will be the axis? Excite 1, okay, you can say this is if you excite 1, right, and if you excite 2, which will be the axis? If you excite 2, right, excite 1 2, it can be somewhere here, no, 1 2, right. and you can reverse the direction also. So, you can create the fields appropriately. Okay. Now, let us say what is the torque acting on the rotor, okay, in the plus theta m direction. What is the torque acting on the rotor? If you excite with phase 1 excited, okay, with phase 1 excited, okay, only phase 1, that is, this is the one, at different position it will experience a torque, is not it. So, at 90 degrees theta m, what will be the torque? Tell me, what will be the torque experienced by the rotor when the theta m is here, this is excited, when this is 90 degrees? What will be the torque experienced by the rotor? What is torque experienced by the rotor when it is 0 degrees? When the rotor is 0 degrees, because 0 is, your measure is aligned here, what will be the, when will the torque be? I hope you understand that torque experienced by the rotor will depend upon the rotor position when phase 1 is excited. How do you expect it to vary? In which pattern? Sinusoidal. So, now if phase 1 is excited, this is one excited, and you know that at 0 degrees it 0 degrees it will experience the maximum torque. It is 90 degrees with the magnetic axis. At 0, when the rotor is at 0 degrees, it is at quadrature to the stator magnetic axis. So, it will experience the maximum torque, it will try to pull into synchronism. Then when it is already reached, it has already reached 90 degrees, it will not experience any torque. So, the combination, so it will change like this, okay, and then it will if the rotor is moved in the other direction, okay, if it is rotor is moved in the other direction, it will get pull it back. So, torque will be, say if it is 0 it will experience, supposing it is somewhere here, if the rotor is somewhere here, so it will experience a torque in the opposite direction, when it is here it will experience torque in this direction, is not it? Okay. Is it clear? I am confused, or you are confused? No? Okay. Therefore, it will, when it is at this position of 180 degrees, it will produce a maximum negative torque. It is trying to pull it back, okay. Then it will go back, and again it is 270 degrees, it will not experience any torque, again go back to 360 degrees, like this you can say, because it depends upon what you have, okay. Now, this is phase 1 and phase 2 excited, it will have a another, this is with rotor permanent magnet, this is 2 excited, okay. So, rotor permanent magnet, that is here, if rotor is variable reluctance, then it will be different. In variable reluctance, if phase 1 excited, this will be the curve. Do you understand that there is a difference between the permanent and variable reluctance in terms of the experience of torque? Because if it is permanent magnet, okay, now this is magnetized, means it has become, this becomes a north south pole, let us say. supposing by putting this, it is like a north south pole. Now, the two magnets will repel, right, okay, according to that. So, it will, because the rotor is magnetized, it will experience positive torque in one angle and negative torque in another angle. So, it will go through a one cycle for 360 degrees. If a variable reluctance rotor is not magnetized, right. So, it can attract to either Sn or Ns. Rotor is a dead bar which can be attracted to the stator field, whether it is in 0 degrees or 90 degrees or theta degrees or theta plus 180 degrees, right, same. So, you will see that whatever is the torque at any position, then it will be same, see, at this position it is the torque, at after 180 it will be the same torque, whereas in this case the torque will be after this position, it will be opposite to this. Okay. Supposing at this position PM experiences this torque and after 180 degrees, okay, this is the torque which will be opposite to this. This is a plus torque and this is a minus torque. Whereas in the case of VR, the same torque is experienced. Okay. So, there is a difference between the PM and VR performance in terms of the torque experienced for a given theta, okay, and the variation of torque. And obviously, if the same thing will happen with two excited, it will be the torque will be different, experienced will have this pattern. So, I want you to, because there is a difference between the PM motor and VR motor, the torques. So, I want you to just verify and check this, right. What we are trying to say is, if you have a rotor, if a stator is excited and it will experience 0 torque when they are aligned and maximum torque when they are unaligned or a quadrature, but in between it will, that will be coming from maximum torque to 0 torque in a sinusoidal fashion, right. So, rotor is experiencing different torques at different theta for a given excitation. Okay. Okay. Now, we have the one important characteristics of the stepper motor is as follows. That is, you have a stepping rate, some frequency, okay, and supposing it is a very low 0 stepping rate, means it won't change, it will have a, it can hold a maximum torque, okay, it can hold a maximum torque, but it has some other stepping rate, say, okay. When you hold to that stepping rate, it has certain pull-in torque. I hope you know what is a pull-in torque. Pull-in torque, that is the torque which it can pull in. You have a, okay, which can, you know, you run it at that speed. So, there is a maximum torque it can pull in, right, okay, to that speed, right. Now, if you, that means it is already there, before that it can pull in the torque. Now, at the same speed, if you can go on applying, suppose it is running smoothly with a pull in torque, maximum pull in torque, right, then you go on adding torque to that, okay, it will still run, no problem, okay, go on adding torque, then it will go to another point beyond which it will goes out of step, okay, and you know that is, this is the pull out torque. If you put the pull out torque at the beginning itself, it will just not start, the machine cannot pull in that torque, okay. So, there are these two torques you must know at any given frequency stepping rate, there is one pull in torque, there is one pull out torque, okay. and you can at 0 it can be, it will be 0 frequency. You go on increasing the frequency, okay, and then there is one point where there is a maximum pull in rate, right. That means here it can pull in 0 torque, okay, almost it can't pull in any torque, you can say, at this position. After all, what's frequency, you go on increasing the frequency, rotor is find it more and more difficult to get pull in, right. And then at this it can still it will have a pull out torque, okay, and there is also a maximum pull out rate. Now this is, but there is the difference between the two, pull in torque and pull out torque. I hope you know what is pull in now. Pull in torque is the one, here what will happen, this is a nice range where it can start, it can stop, it can reverse, all these things it can do, healthy range, this is a response range. See, if this rate at this point, this torque, it can start the motor, it can stop the motor, it can do that, but here it can't do anything. Only thing it happens in this range, if it is running, it will continue to run, right, otherwise it will go out of step. So this range is called a slew range. Slew range is the range between the pull in and pull out, right, which it can't do any changes, okay. So this is important characteristics. Of course, there are also ranges of instability. For some ranges, in fact sometimes you may see there are some ranges it may become unstable also. I hope you know stability. All of you have studied stability in several courses, mostly in control system course. You must have done stability in electronics course also. Do you have stability in electronics? Power system stability, okay, mechanical stability, okay. What is stability? What do you call stability? Why do you say something is stable? Because the system is operating, is stable. No, why, when do you say it becomes unstable? Yeah, the thing, if there is any disturbance, it can't, it will not follow, it will go back, it will not go back to its equilibrium position. It is in equilibrium position, in a disturbance it gets out of equilibrium, right. So that is why a system is considered stable, but most of you are mathematically very right, but then when it comes to concepts it becomes a problem. That is why even a person is considered to be stable, whether he is in equilibrium if it is under disturbance. If you disturb him, he will still be in equilibrium. So he is a stable person, okay, right. Of course, sometimes he is too stable, means he may also be dull also, right, okay, right. Now this is important for you to know in a system, okay. So pull in torque is you have you put some torque, okay, which you can pull into that step, okay. When you are even in any machine, even synchronous machine also, you can, or a reluctance machine, when it is running up to certain torque it can pull in, after all there is some static torque is there, okay, and that much torque it can pull into synchronism, but ultimately at that speed it should run it, supposing at this rate, supposing give this pulse rate means it should be capable of rotating at that speed, isn't it. What is pulse rate? Stepping rate in frequency, okay, and that speed, if it is low then you can pull in more, right, up to that speed. After all it is running at some point, okay, you want to increase it, then it cannot, it will, you have applied a torque which it will pull into synchronism, with that torque. If it is no torque, it will easily pull into synchronism. More torque, it will take some time, some efforts, etc. Okay. So that is why there is always this torque is pull in torque and pull out torque is very critical aspects. Okay. So pull in torque characteristics called the starting characteristics. That means you start the characteristic range of, that means it is typically it will consist of its frictional load torque. What is pull in torque? It is whatever it can pull in, right. I mean, how does the scooter or car start? You see, there is already something which is dead, passengers are there, it can pull in still. If too many people are there, it can't pull in, okay, then you have to push from behind, okay, right. So, this is what you can pull it and it can run, okay. Now, the thing, if it is running, you can have a more torque also, right, and but then again you overload people sitting on the top, etc., on a truck, then some stage it will collapse and get into a river or something, okay, okay, right. So, instability will come to the picture, right. So, these are the characteristics, okay. So, there is a range of frictional load torques, okay. So, motor can start and stop. See, a bus, I think this practical thing you will be able to understand. I think it can start, stop, and it does not lose steps, okay, and whatever frequency. You can say frequency is like even the speed of a bus or a car, okay. So, that these are the things it pulls in, okay, it is very stable. Pull out characteristics is also called as slew characteristics, that is relation between the frictional load torque and the maximum pulse rate, which is the motor can synchronize, okay, and this is called the pull out characteristics. It can synchronize, but beyond which it cannot go, okay, this is called the pull out characteristics, okay. So, because this we have already seen, I do not want to repeat, step angle, step number, these relations we have done that, okay. Then smaller the step angle, the higher resolution, etc., we have seen, and position accuracy we have also seen. I think it is a repeat of the same thing which we have already done, quality of stepper motor, etc. Okay. High restoring torque is produced when a displacement from rest position occurs due to a load torque, okay. When the load torque, restoring torque, that is what you are saying, okay. I think there is a position accuracy, of course we have also seen that, okay. Step position error, I think this seems to be a repetition, position accuracy, okay. Now, this is important. What is important is high torque to inertia ratio, right, this is very important, okay, because this is all dynamically operating. Ratio of torque to inertia must be large in stepper motor as compared with conventional motors, okay, because they always work in dynamic situation. It must produce high torque and low inertia, okay. That is one of the things that you need to have in stepper motors. Now, how do you select the motors? How do you select a stepper motor? Okay. How do you select anything? You have something like a rating, okay. You have something like how do you select a classroom? You must know how many rating, how many students can sit in that room, okay. So, stepper motor, what is important is the torque, deliver enough torque to operate the system, right. It should have enough torque to operate the system, okay. Now, how do you decide what torque, okay, to operate the system, okay. Now, the total torque will be load torque and inertia torque, is not it. There is a fixed load torque, there is a inertia torque, okay, and that means torque must be sufficient to start the motor, to run the motor and stop the motor, right. In this case, it is just not that it can just run. Now, where is the inertia torque becoming predominant or important in the three modes? So, here you have inertia torque, here you have the inertia torque, is not it, right. when it is running, it is just a Newton's law of motion, you do not need no disturbance. It has when it is in continuous motion, all that your accelerator should do is just to make sure that it just takes care of the friction torque, okay, load torque. Now that means the system torque demand. So you have starting and acceleration. This is one this thing. Now what is the torque demand by the system? Now in the starting you have the load torque, at starting, and there is inertia torque also at starting, okay. That means you have a dx by dt or d theta by dt, d square, j d square theta by dt square, j omega, whatever, okay. This is the torque demanded by the system, and then running at constant rate. Now this is, you have a constant switching rate, it is running, okay, at some speed. Then what will have, there is a load torque, running torque, and there is a difference between the static and running. You know the static and running frictions are different. There is one static friction and another running friction, there may be a minor difference, and here no inertia here, okay, no inertia torque. So it is nicely running up to this. Now I want to stop, okay. How do you stop? What is stopping? You are killing the kinetic energy, you are destroying the kinetic energy to come to 0, okay. Now there, even in stopping there is inertia torque, okay, and there is a running load torque. Now this is the torque demanded by the system, and this is the torque provided by the system. See, load torque, now the directions will change. When it is stopping, the directions of these two torques will be different, because your external torque is 0, okay, and whatever is the inertia torque is feeding onto the friction torque, okay. When you stop a motor, what will it do? There is inertia torque which will just supply the friction torque, okay. So this is one thing you need to know, okay. So yeah, now we will 2-3 minutes I will take, okay. So this is I hope you understood the 3 modes of operation, okay. Whereas in one mode all the torques have to be provided by the motor, other mode the motor torque inertia, regeneration is there, okay. Now this is an example of a positioning system, okay. How a practical system works? Here is a stepper motor, and here is the coupling, this is the gear, okay. Now as you rotate this, there is a lead screw here, and then it will move the table on which there is a workpiece, okay. Now so as it rotates, it will move the table, right, either this is a screw, so it will move it in this direction, okay. Supposing this job is given to you, so you have to find out what is the capacity of the motor, right. So you have to find out the inertia and you have to find out the load torque, isn't it. So obviously inertia, all this thing will get translated, inertia will be a combination of all these bodies, this mass is there, this mass is there, then there is this work, etc. So in fact incidentally in this paper I told you, he has explained how do you calculate this, that is why you refer to this paper. He has given this example that there is the inertia of the cylinder, okay. There is this acceleration, after all when it accelerates what should be the torque, etc. And what will be the total T inertia, okay. So these are calculated based on, you need to have all the parameters of the mechanical system to find out what is the inertia, what is the load torque. Okay. And these gears also get this inertia get translated like a transformer ratio, there is a gear ratio. Okay. I think you must have done something in mechanics course or whatever you must have. Okay. So, these are the how you calculate the torque. So, you must calculate the torque, you must calculate J for this purpose. I mean this is one example of a practical application of a stepper motor which moves, right, and the continuous rotation is not so much, mostly it is a step change of movement, etc. So, we have given you a glimpse of what is a stepper motor, what are the factors involved, what are the constructional features, what are the type of stepper motors, what are the mechanical features, okay, angles, accuracies and so on. And this is not the end of stepper motors, and if you want to know more, you can go to websites, we can read lot of things. So, this is only the first step in the study of stepper motors. Okay, we will close it here.